Okay. Hi everyone. Happy Tuesday. Very glad to welcome you to another installation of the Paleo Perks seminar. And today we have Zekun Wang from the Natural History Museum in United Kingdom. And today he will be talking about quantitative ichnology, unraveling biological signals from trace fossils during major evolutionary events. But before we get into the talk, for those of who you are new, we will quickly go over the format of today's seminar. So first we'll have welcome and announcements, which is ongoing. Then we have the talk for 30 minutes and followed by a moderated question and answers. Do not forget to send your questions via chat to the questions at PaleoPerks host, who today is Nina. A bit of housekeeping. Paleo Perks values the participation of all folks interested in paleo sciences. Please remember to abide by our code of conduct during today's seminar. Please mute yourself for the duration of the talk out of respect to the speaker. You shouldn't be able to unmute yourself, but in case you do, please mute yourself. You can ask questions by chatting to the questions at Paleo Perks host or by using the raise hand function. If you face any technical issues in your Zoom room, please also approach the questions at PaleoPerks host. We have closed captions built into Zoom. Use the CC button to show or hide them. PaleoPerks runs on the nominations of excellent early career researchers like our speaker today. So please try to nominate an outstanding researcher the link to the form will be dropped shortly in the chat. We also collect anonymous weekly feedback to gauge the demographics of our audience. This is completely anonymous and optional, but it's encouraged that you also respond to this form, and the link will be dropped in the chat shortly. Now, to introduce today's speaker, Zekun Wang. Zekun did his BSc in Nanjing University of Aeronautics and Astronautics in China. Then he did a PhD in Peking University in China. And currently, Zekun is a UKRI Fellow at Natural History Museum in the United Kingdom. Zekun, all over to you.
Okay, thank you. So I can share the screen now.
Yes.
Yeah, great. So when we go to a museum, we can see all these big dinosaur skeletons, a list bird, or the list flowers. These are all the body remains of these organisms, so they are body fossils. And these body fossils provide unique insights into the evolutionary stories of the animals in deep time, including the evolutionary radiation, the massive extinctions. But there is another type of fossil, we call it trace fossil, which are the fossilized interactions between the organisms, including its anatomy or behaviors, as well as its environment, including the substrates, the fluid flow or predation pressure, etc. So these are big dinosaur trackways or the burrows, borings, invertebrate trackways, eggs, poops, or nests, they are all fossilized interactions between the organisms and its environment, and they are all trace fossils. Similarly, these trace fossils also provide unique insights into the evolutionary history of the locomotion, anatomy, and behavior of the trace makers through deep time, because these trace fossils actually they appeared very early, over half billion years ago, which is approximately maybe 565 million years ago, and they also experienced abundance, a great abundance and diversity during the Cambrian explosion. So these trace fossils are very important. I mean, the trace fossils of the marine invertebrates, okay, not the dinosaur footprint, but they are also important. So these invertebrate trace fossils are very important because they filled in the gap between in some geological period where the body fossil record is patchy and incomplete, especially during the Cambrian, Ediacaran and the Cambrian transition, during which the body fossil is really patchy. So, but the trace fossil is very abundant with high diversity, so it's quite important to study the earliest animal evolution during that interval. But on the other hand, some trace fossils also appeared much earlier than their putative trace makers, like the Cruziana or the Rucificus, which is the locomotion and the resting trace of the trilobite. They appeared much earlier than the earliest record of body fossil of the body fossil of trilobite. So with this trace fossil record, we can study, for example, the evolutionary history of these of certain behaviors, body plans, tearings during the dawn of the animals, the earliest animals during the current Cambrian transition. So they are really very important. But there is some huge challenges in the study of trace fossils, which is lack of quantification. So it is a little bit subjective. This is further sophisticated by the fact that there is no one-to-one mapping between the trace makers and the trace fossils. For example, one trilobite, it can create different traces under different environments or on different substrates. But animals from absolutely different phyla, like this sand fleet or the mud snail, they can create similar traces, at least judging by naked eyes. So this poses great challenges to the biological interpretation of these trace fossils through deep time. Therefore, our present study on trace fossils are based upon some qualitative analysis. For example, our classification of trace fossils can be is based upon the behaviors. Some trace fossils are classified as some foraging traces, or of grazing traces, or their living, their host, we call it domicilia, or the parenting or farming traces. So it's all related to behavior. And another classification is related to the topology. We call it architecture design, whether it is a U-shaped burrow with or without sprites, whether it is a radiative shape, whether it has a radiative or rosette shape, whether it is a branching burrow or a simple horizontal locomotor trace, whether it is a reticular or a network trace, something like this. It's all topological or architectural design. And another type of interpretation of trace makers or trace fossils is related to the functional groups. So if whether the trace makers are live on the uppermost surface of the sediments, we call it a surface modifier. So if they are meiofaunal bioturbators, meiofaunal trace makers, we call them meiofaunal bioturbators. Some trace makers can also generate or move their sediments vertically, so we call them, for example, the regenerators. So these classifications or interpretations of trace fossils are very useful, and they are the basis of traditional ichnological studies. Ichnology is a discipline to study trace fossils. So, is there any quantitative method that can help us better quantify for example, the morphology or the evolution of trace fossils, especially those simple horizontal locomotor trace fossils without very complicated superficial textures? So today, I will introduce some methods, and I will divide the talk into two parts. The first part is the analytical or statistical approaches, the mathematical matrix to describe trace fossils. And the second part is a numerical simulation using computers. So in the first part, I will introduce frequency analysis, smooth analysis, and integral scale. And in the second part, I will introduce a small foraging program and the coupled CFD-DM simulations that can help us reproduce the formation process of trace fossils. So let's begin with the first part of the frequency analysis. Okay, in our daily life, as you can see, there are so many signals, including the sound, the wind speed, the image, or the even the price of the stocks. We also use different kinds of signals in deep learning or data compression. They are all signals. So these signals tend to evolve with time or distance. So we call it a temporal, or they are in a temporal or a spatial domain. For example, this signal, which is a sign, another the two sign. So you can see there are two major frequencies. The first one is 0.5, and we can calculate the period by the inverse of frequency, which is 2, and there is another frequency which is 2.5, and therefore the period is 0.4. So it actually has two different order or two different self-repeating patterns in the signal. So after we do a Fourier transform to convert the signal into the frequency domain, you will see two peaks in the frequency spectrum, which is zero point 0.5, the first frequency, the first order frequency, and 2.5, the second order frequency. So how can we use the Fourier transform to interpret the trace fossils? So what is a signal we should use to for analysis? Can we use coordinates? No, because coordinates can seriatically be unbounded. It can be infinitely large or infinitely small when the tracemaker moves away. So can we use the angle with respect to the origin point? No, because when the tracemaker moves towards a certain direction, this angle will converge to a constant, and the signal is compressed, so it's also problematic. So we will use the turning angle to left, anticlockwise, or clockwise these turning angles to analyze the trace fossils. So first of all, we need to digitalize the traces, no matter it is a trace left by modern organisms, in modern observations, or it is a trace fossil. It doesn't matter. We need to digitalize it first and extract the coordinates along this trajectory. Then, to get rid of the size effects, well, based upon the hypothesis that the animals, regardless of its actual sizes, if they are from the same taxa, they will leave traces with similar topologies, similar geometries. So, to get rid of the size effects, we will normalize the trajectory. It means when we talk about the length, we use the normalized length, which equals to the length divided by the actual length divided by the actual width. So if the normalized length is 10, it means the length is 10 times of the width at that point. Then we can use the vectors, the unit vectors, and the inverse trigonometric functions to calculate the deviation angle or the turning angle between two sampling points. And according to the right hand rule, when the organism is making an anticlockwise turn, you will get a positive turning angle. This is because the Cartesian coordinate is established based upon the right hand rule. Okay, when you, for example, make a cross product between the x-axis and y-axis, so it is an anticlockwise turn. And according to the right hand rule, you will get a z. You will get a positive z direction. It is also the same with the turning vector. So in order to calculate the turning angle vector, so we will do a cross product between the radial vector and the tangent vector. So if you are turning anticlockwise, you will also get a positive value along the axis. So if the tracemaker is turning anticlockwise, you will get a positive turning angle. So let's take a look at the traces left by some modern analogs, then make some comparisons with trace fossils later. So for example, for the traces left by isopod, it's a small and also a round shape, short-bodied arthropod. As you can see, there is no major peak in its frequency spectrum. This means there is no self-repeating patterns in its trajectory. It's a little bit random. But if it is a trace left by nematode using undulation to move, then you can see there is only one major peak in its frequency spectrum, and the major frequency is around 0.075. Then we can calculate the period, which is the inverse of frequency, which is around 13. This means the length of a full undulation of nematode is around 13 times of the body width, which is actually around the body length of the nematode. So for polycase, this major frequency is much smaller because it make large loops. And for gastropod, it's a little bit different. It has 4 to 5 different major frequencies. This means it is a 4 order or a 5 order curve. It means it is a fractal curve. It has a hierarchical pattern. It indicates the kinesis of the tracemaker. So kinesis means frequently changing moving directions or moving speed in response to the change in the density of stimuli. So this is an ecological tendency characterized by the grazing organisms or those detritus feeders, because they need to produce a space filling curve to enhance their foraging efficiency. Okay, another approach is autocorrelation function, which is calculated by this formula. As you can see, the delta L heuristic is it tells you, okay, the autocorrelation function informs of the correlation between 2 points along a signal, whether they are correlated. So the delta L heuristic is a dimensionless distance between these 2 points. When it equals 0, you can see the denominator equals the numerator. So the this autocorrelation function is 1. That's the maximum correlation. When the 2 points are far away from each other, they can either have the same sign, the same turning direction, or different turning direction with the same probability. So after taking an average, you will get a zero value for the autocorrelation function. So when the 2 points are close to each other, they can have statistically speaking, they should have similar uh, turning degree, turning angle with the same turning direction, statistically speaking. So after taking average, you will get a value between 0 and 1. So this autocorrelation function should have a generally decreasing trend eventually to 0 when it is far away, when the distance between 2 points is far away. So for arthropod, you can see this it experiences a very sharp and abrupt decrease in autocorrelation function. So it means it decolerates very soon, very rapidly. And we can define a characteristic autocorrelation function, autocorrelation scale, which is the first minimum value of the autocorrelation function. And this is around 1.4 for isopod. This means an isopod can make a very sharp and abrupt turn only within 1.4 times of its body width. That's a very sharp turn. And for nematode, as you can see, this characteristic autocorrelation scale is around a 6.45. This is exactly half of the major period we calculated from the frequency spectrum. This is because in a full undulation, it has two curvature of opposite directions, of opposite turning uh, sign of positive and negative according to the right hand rule. So when it enters the second part of the undulation, it decolerates because the sign changes from, for example, positive to negative. And for polychaetes, this is much larger, and for the gastropod, it's smaller. So this scale actually informs of the maneuverability of the trace maker. So we can take a look at some trace fossil record. For example, these trace fossils are some Gordia trace fossils. So the Gordia is characterized by the self-crossing of the trajectory. So the first one is Gordia nodosa. As you can see, it resembles the traces left by some polychaetes. And the second one is a Gordia indonesiense. Although this taxa is not valid anymore, but still you can see a lot of these relatively randomly self-crossing traces left by arthropod. So this kind of trace fossil should be left by some short-bodied arthropod. And the third one is Gordia marina, which could be related to some mollusk grazing behavior or the feeding over the carapace of some dead animal. And the last one is also Gordia marina, but it should be probably left by some nematode or animals with similar locomotor mode. So as you can see, the frequency spectrum and autocorrelation function can serve as the identification card of these trace makers, and it can help us take an estimation of the trace makers through deep time. And we can also make some comparisons between the trace makers and their trace fossils through deep time. And some of the trace fossils actually appeared much earlier, not much, at least a little bit earlier than the trace makers. But we can also use this matrix to do the classification of trace fossils, the ichnotaxonomy. As you can see, for the traces, the Gordia traces left by arthropod, it has the smallest the x-axis is the characteristic autocorrelation scale, and the y-axis is a major frequency. So for the Gordia traces left by arthropod, as you can see, it has very small characteristic autocorrelation scale, which is 1.4, and it doesn't have a major peak, so it spans a very wide range. The major frequency, the y-axis, it spans a very wide range. So similarly, for Gaudium marina left by gastropod, it has a relatively small characteristic autocorrelation scale, and it has a 4 or 5 major frequencies. So as you can see, each Gaudia ichnospecies occupies a unique region of the face map with its unique shape. So we can use this for iconotechnique. Okay, the second matrix is a smoothness analysis. The smoothness analysis is related to the trajectory smoothness, which means whether it has continuous derivatives. But this continuity derivatives can also be applied to surfaces. So in that case, it's related to the roughness, sufficient roughness of the walls or the boundaries of the trace fossils. But in this talk, we will only talk about the continuity of derivatives of a curve, which is a trajectory smoothness. So in mathematics, we can actually very rigorously to define the trajectory smoothness. So if a curve is smooth around a point A, then we will have this definition. Okay, for all randomly extremely small positive value epsilon, there always exists a tiny length delta such that whenever the distance between the 2 points A minus and A is smaller than delta, you can always have their deviation angle smaller than epsilon. So it is smooth around A. This means when the 2 points approaches each other along a smooth curve, their tangent line will eventually overlap. Then it is smooth. Okay, for the second figure, if it has an abrupt turn where there is no derivatives, so it is not smooth around A, no matter how close these 2 points are, their tangent line will never overlap. And there all will always be an angle between the tangent line of these 2 points. So it is an abrupt turn. It doesn't have a derivative at this point, so it is not smooth. Then we can classify the trace fossils into smooth traces and originally smooth traces with a limited number of abrupt turns, and utterly smooth traces, utterly unsmooth traces. But this is a pure analytical approach. So we need some kind of a matrix to actually quantify the degree of smoothness. So we use a proxy, which is the minimal radius of curvature. The radius curvature is the radius of this circle that is closely attached to this curve. So if it is a arm smooth trace with an abrupt term, so seriotically speaking, the radius of curvature at this point without a derivative should be 0. So it can actually help us detect whether there is an abrupt turn in the trajectory, thus unsmooth. Okay, so the minimum radius of curvature is also useful for the detection of abrupt turns and unsmooth trajectories. And another proxy is the spectral density. So as you can see, spectral density is calculated by this formula. So if it is a smooth trace, like this trace left by the acorn worms, then there is basically no high frequency components in its spectral density. This means there is no small scale, zigzag, shaky, unsmooth, abrupt terms. It is purely smooth and large scale smooth patterns. But for this trajectory left by foraminifers, it is very unsmooth with so many zigzag and small scale unsmooth abrupt terms. So there is so many high frequency components in its spectral density. And high frequency spectral density means a small scale, zigzag, shaky, unsmooth terms. Therefore, we can define the power, the signal power used for unsmooth locomotion by integrating the spectral density from 0.5 to 1, the latter half of the spectral density. And we can also define a smooth index, a smoothness index, by 1 minus the ratio between the power used for unsmooth locomotion and the total power used for smooth for locomotion. So if the trajectory is very smooth, then there will be very low unsmooth components. Therefore, it will approaches one. Okay, it will approaches one. Then we can take a look at the trace fossil record during the current Cambrian transition. As you can see, for the traces before approximately 145 million 545 million years ago, the traces are basically all arm smooth, characterized by this plotted by these blue dots. So these unsmooth traces tended to have very small minimal radius curvatures due to the existence of abrupt turns, like some traces left by foreigners. So, so these traces have abrupt turns. This means the trace makers should have a very short body profile, maybe a round or ovoid shape, so they can make very random changes in orientations at where they are. So these abrupt turns. But approximately after 540 million years ago, those regionally smooth trajectories appeared. So these trajectories should be left by organisms with anterior posterior axis, with musculatures, and also kinematic coordination of the muscles and hydrostatic skeletons to help them maintain the direction, at least locally. So they can be, for example, some short-bodied arthropod or short-bodied mollusk. Almost at the same time, purely smooth trajectories appeared, like these Cotylicnus. Well, some people don't think they are called Cotylicnus because there is a loop, but in any case, they are smooth trajectories, and they are probably left by some slender worms using undulation for propulsion to move. And these organisms should also have an evident anterior posterior axis with musculatures and also kinematic coordination of the muscles. They should also have, of course, hydrostatic skeletons. So these are the deep root of Cambrian explosion, right? Then we can take a look at the power used for high frequency unsmooth locomotion. As you can see, this power for unsmooth locomotion is very high for trace fossils statistically before 545 million years ago. It means they are very unsmooth, and they become more and more smooth through time. It means they have higher locomotory fluency, behavioral fluency, and also probably a slender body. But we also did some numerical simulations, which we will introduce later, and we find that the increase in perceptual range will also lead to a decrease in the power used for unsmooth locomotion, which means it will become more and more smoother. So this indicates that the organisms during the Decarian and Cambrian transitions have gained a longer and a longer perceptual range. They can sense things from far away. And these organisms indicate a very deep root of Cambrian information revolution. And these organisms actually transformed the substrate from a two-dimensional, relatively homogeneous, microbial matter-dominated and also diffusion-dominated substrate to a three-dimensional mixed ground, which is very patchy and dominated by the advection. Okay, so these all are the evidence of very deep root of Cambrian information revolution. But a smooth analysis can also be employed to the ichnotechnomy to classify trace fossils. For example, there is only one valid ichnospecies within the simple horizontal traces Homisoid ignitis, which is Homisoid ignitis tenuis. But actually, in practice, we will have both smooth and unsmooth components. But as you can see, the smooth trajectories should be left by some kind of slender worms with relatively long range sensation, but the unsmooth ones should be left by some maybe short arthropods, tiny arthropods, right? So statistically or theoretically speaking, they should be classified into two different hemisoid ignitis. Similarly for gold, yeah? Okay, then we will have some discussions about the integral scale. So we have seen the increase in body length during the current Cambrian transition, but how long exactly they were was still unknown. So I will introduce the integral scale of the magnitude of curvature signal to compute the minimal body length. So the integral scale is is computed by integrating the integration function of the magnitude of the curvature signal. So it tells you the minimal scale over which the turning angle maintain a structured pattern, maybe a curvature. So we use the magnitude of the curvature, which is the inverse of the radius of curvature, and is related to the anatomy and is related to the biomechanical constraint of the tracemaker. So how sharp it can turns tells you the integral scale. Then we can collect as many observations as possible where but in these observations, the animals has to be simultaneously observed or preserved with its trajectories. So we can measure the animals, their locomotor unit, and all the body lengths. And eventually, we can find out the scaling law between this integral scale and the normalized size of the characteristic locomotor structure, which can be the normalized size of an independent locomotor, or the size of a group of locomotors coordinating for the same direction. Then we can have this, then we find the scaling law between these two parameters. As you can see, there is a strict proportionality between the characteristic length for locomotor structure and the integral scale. For animals with discrete, uncoordinated locomotors or extremely small locomotors, like some forans or sea urchins, okay, they have very small characteristic locomotor lengths compared to the body width or body size. Therefore, they have very small integral scale. They have the highest maneuverability. Then followed by animals with discrete but coordinated locomotors like some arthropods. Then followed by animals using undulation, peristalsis, or one-order bending for locomotion. So actually, as you can see, these two parameters characterize the maneuverability of the tracemaker, which is determined by the size of its locomotoring units. Then we can take a look at the trace fossil records through the Cambrian transition again. But it should be noted that the characteristic locomotor structure should always be smaller than the body size. So this parameter actually helps us predict the minimal body length. So as you can see, the trace fossils from relatively early terminated carrion all have very short body sizes, minimal body sizes, which is around 2 or 3, which is ovoid shape. And it reaches around 8 at the Cambrian transition boundary, and it reaches around 12 in the early Cambrian, for example, in the Schiento Formation. So these organisms have undoubted slender anterior posterior axis, as you can see, and this should be modulated by, for example, Hox genes or colligams, and these organisms should also have a rigid body, which is ensured by the Euler-Bernoulli equation. As you can see, this rigidity, which is a product of the Young's modulus E and the moment of area, this is rigidity. So with the increase of rigidity, the radius of curvature also increases, which leads to an increase in integral scale. So the increase in integral scale also informs of the existence of a rigid body, probably equipped with musculatures, cuticles, and a stable hydrostatic skeleton. So this slender body will also facilitate a directional movement and enhance the dynamic stability, and also reduces the drag from either fluids or the substrates. And an increased body sense, increased locomotors will also give them a larger gait, which will enhance their mobility and help them explore a wider ecospace, and set the foundation for the Cameroon substrate revolution. These land organisms should also have a relatively long digestive tract and help them better to digest this nutrition, which will help them eventually gain a higher position, for example, the niche. And these animals are probably civilized. Okay, Another part is this is a second part. The second part is numerical simulation. So you might wonder, how did I get the smoothness? For example, the smooth index or the power used for unsmooth locomotion from the perceptual range, the variation perceptual range, because we can't measure perceptual range from either modern organisms or a fossil record because I did numerical simulations. So there are three different ways to for scientific researches. The first one is seriatical. For example, the epsilon delta definition for smoothness, or the Unravelling equations. So these are series theoretical studies. And another approach is statistical, including experiments or the study of fossil records or artificial intelligence. These are all statistical, including the frequency analysis, the frequency spectrum or calculation function. And the numerical simulation is between the theoretical and, and statistical approaches because it uses the basic series, the basic formulas from simplified series, and input them into the computers. And the computers help us to compute things. And the output data can also be used for statistical analysis. So I
Uh,
actually have a
Second,
computational
uh,
mechanics background.
hi,
So these are some
Zekun.
simulations. Yeah.
Sorry, we are already at the 30-minute time. So
Yeah,
just
I
giving
will
you.
finish in 5 minutes. The second
Okay,
part is
thank
very
you.
short. Yeah,
Yeah.
yeah. So these are some simulations. For example, the merge of galaxies, or the filter feeding of organisms, or the similarity in the wake behind a trilobite. So what about the trace fossils? First of all, for example, we can do some foraging program. As you can see in this program, the forager, the animal, it moves along the maximum gradient of food or stimuli, and then we can change the body size, the food density, the collection rate, or moving speed, and even the perceptual range of the trace makers, and the test and the perceptual range is a range within which the organisms can sense the food. So we can make some changes over these parameters and see how the topology of the traces changes and study its smoothness or randomness or etc. And the second part is uh, coupled computational fluid dynamics and discrete element method, in which the organisms is modeled by, for example, the Euler angles, and the sediments are modeled by real particles dominated by the Newton's second law, and the fluid, no matter the gas or the water, is computed by the Navier-Stokes equation. Another simplified method is to use the non-Newtonian fluid to represent the substrate instead of the numerous particles, like for example, the Bingham plastic. So with these approaches, we can numerically simulate the formation of trace fossils of traces in different environments. For example, these are the three traces formed in different environments by a limpet. This is a trace formed underwater on non-cohesive sediments. So you can see a very wide levee, a relatively low relief, and a very smooth levee. But if it's formed on EPS infused non-cohesive sediments, so these sediments becomes a little bit cohesive due to the existence of EPS, and the relief is still low, but you can see there are some unstable shapes, unstable geometries in the leaves. But if it is formed in a subaerial environment on wet sands, as you can see, there are very sharp, even concave morphology of these leaves, and it has high reliefs. So we can test the environments and test, for example, the moving speed, the trace makers, or different depths, and see how they affect the results. And with these results, we can do some analysis. For example, we can establish a scaling law between the variance of the levy width and the moving speed, and make some predictions about the trace makers. So in today's talk, I introduced some quantitative methods for the trace fossil analysis, and also talk about the significances of these analysis, including the frequency analysis, the smooth analysis, the integral scale, and eventually I talked about the numerical simulations using computational fluid dynamics and discrete element method. that can help us reproduce the formation process of trace fossils. So eventually, I want to establish a framework where we can use the biological and the sedimentological signals to do simulations or dimensional analysis, which is a kind of a very complicated mathematical analysis. And eventually, these analysis will help us get some quantitative matrix like smoothness, randomness, fractal index, or the frequency analysis. All these quantitative matrix can help us analyze the relationships and the scaling laws between the geometry, biological, and seismological signals. And we can use these scaling laws to analyze trace fossils and obtain new insights into the biological or sedimentological interpretations of these trace fossils through deep time. Okay, and here are the four papers I talked about in today's talk. So the codes and the free software of the frequency analysis is released in Zenoda with a paper published in Paleontology, and the second version of this free software is uploaded in the Zenoda again, which is related to a paper that is to be published in Proceeding B very soon. And these are another two papers. Okay, thank you. That's all.
Thank you, Zekun. That was an amazing talk. We already have some questions in, but as a reminder to the audiences, some of you may have a new Zoom update. So if you were not able to send your question, uh, or you don't see your question come up during the session, just feel free to put them on the chat or raise your hand, and then we can unmute you to for you to ask your question. But we will start with the questions that we already have. So Karthik Sendur is asking, how do you accommodate for biological variability in the length of an organism, making a locomotory trace fossil, and sediment infilling slash diagenesis while computing the turning angles?
Excuse me, means can you repeat the question?
Yeah, I can repeat the question. How do you accommodate for biological variability in the length of an organism, and also infilling or diagenesis when you're computing the turning angles?
So okay, for the diagenesis, it means turning the fossil into rock, right?
Hmm.
Yeah. So this main also it's a little bit complicated. For example, when the rock is stretched or compressed, for example, the smoothness will not change because it is an inherent nature of the continuity of the trajectory, and this continuity of the derivatives will not change under uh, we call it some kind of a spatial conversion, like the compress or the stretch. So for this kind of deformation, uh, the smoothness will not change. It will you see abrupt turns will still be abrupt turns. Smooth trajectories will still be smooth trajectories. But if the sediment particles are relatively large compared to the trace makers, then then uh, you will see some zigzags or some shaky boundaries along the trace fossils, but the main line, the central line of the trace fossil of the trajectory should still reflect the real locomotion of the organisms. Also, I forgot to say also the deformation of the rock will not uh, to some extent to some extent to some extent will not affect the self-repeating patterns. Yeah.
Thank you. I think that makes sense. Thank you for your answer. Dimitri has asked, how do you standardize the resolution and protocol of digitizing the traces? Does that
Okay. Yeah.
affect
The
the
resolution. Yeah.
calculation? Yeah.
Yeah. I attached the details about the resolution. For example, the resolution of photos, or the sampling frequency means how many points I picked within, for example, a width distance in the supplemental materials of this preceding paper. I will give you a brief answer now. So, for example, for the sampling point, normally we need to choose two sampling frequency, two or three. It means within a width length. When the length equals to the width, we choose 2 points or 3 points to measure the central line of the trajectories. It cannot be too dense because if you choose 10 points within a width length, you can't control. You see, you can't control the convexity or concavity of the overall trend. For example, if it's turning clockwise, if it's turning uh, clockwise, and you pick 10 points with a very close distance, and you can't control, you know, manually you can't control it accurately, and it will be zigzag if you pick so many points along very short distance, because it's almost straight, and it will become, the trajectory will become zigzag. It will become shaky. It turns left, then turns right, then turns left, and turns. These are all measuring errors. Measuring errors. So you can't pick too many sampling points. Pick too many sampling points within a width distance, and we recommend, and many ichnologists only pick around 2 points within a width distance. And for the photos resolution, you can use PowerPoint to enhance, to manually change the resolution of the photo. It can be blurred, but at least if you have more pixels, the measuring accuracy can be enhanced. So there are so many details. You can look for those details in the supplemental materials of the preceding paper, this year's preceding paper. It is in press and it will be published very soon.
Thank you. Dimitri, if you have any other follow-up questions, feel free to put them in the chat. Um, we have an anonymous question. This question asks, is curvature in 3D taken into account for example, in burrowing traces? If not, do you plan to perhaps apply your methodologies to CT scans or 3D traces?
Oh yeah, yeah. All these matrix can be applied to three-dimensional traces, but some results will be different because an additional degree of freedom. For example, the frequency, right? If you move in a two-dimensional plane, or if you move in a three-dimensional space, like some three-dimensional burrows, the curvature can be different, but it can also be similar due to the anatomy. So at least for comparison, we need to keep the dimensions the same. We need to compare horizontal traces with horizontal traces. We need to compare 3D traces with 3D traces, but it can be applied to 3D traces. But for smoothness, it will not change if it is kept in a two-dimensional space or expanding in three-dimensional traces. But just keep in mind, you need to make a comparisons within the same dimensions. Yeah, it can be applied to three-dimensional space.
Okay, that's nice to know. So the next question is from Karthik, and he is asking, does the type of sediment in which the organism is moving influence the smoothness of the trace fossil? If yes, are finer sediments correlated with more smooth trace fossils?
Okay, yeah, this is a great question. So, as I said, there are two different types of smoothness. So in this talk, we are talking about the trajectory smoothness, not the surface smoothness of the trace fossil. So we are talking about the smoothness of the central line of the movement. So the central line of the movement should not be affected by the type of sediments because it's just a locomotion. It can, the sediments can change the overall morphology, the overall geometry of the pattern. It can change the overall pattern due to the different resistance, different drags from the substrate, but it can, but as for but for a specific central line, if it moves along a fixed pattern. So this pattern, the central line of the pattern will not change because of the, for example, the radius of the size of the particles. But for the second type of smoothness, which is the smoothness or surface roughness of the trace fossil, for example, the surface roughness of the wall, the surface roughness of the burrow, it can change with sediment particles. For more fine particles, like the clay, so the surface of the burrow will be smooth. If it is very coarse sandy sediment substrate, then the surface roughness increases and the surface smoothness decreases. Okay, that's for the surface smoothness. But for trajectory smoothness, it will not be affected by the nature of the sediments. Yeah, that's all.
Thank you. That was a great answer. We have another anonymous question, and I think this will be our final question for the day. Can you use the numerical simulation to model bioturbation of different sediment types?
Yes, I think I can. I think the problem is maybe to mark, because bioturbation, it can happen for multiple times and the sediments can be reworked for multiple times. So maybe we need to uh, you know uh, mark the sediments, so we will know which time it was formed. Just yeah, we need to mark the sediments. We can do this. Mhm.
Okay. Well, Zekun, it was great to have you, and thank you for answering all our questions, and thank you, the audience, to join us for today and asking your questions, interacting with our speaker. So, thank you all. Please fill out the weekly feedback form, which will be posted in the chat again, so that we can learn a bit more about who attended today's seminar. And we welcome you to join us on July 1st for a panel discussion on science communication. And we'll be joined by science communicators around the world. We have Kate Larson, Tim Pierce, Khalil Tiralwe, and Milo Yates. So ECU on July 1st, and have a happy Tuesday, rest of the happy Tuesday. Bye.